In this video, I'm demonstrating to you the Excel project where we iteratively solve for 5 unknowns in the general triangle problem. So I can zoom in here a little bit. So we previously worked a problem that had a right triangle geometry, where if we hung weights of different weights, this slider would slide down farther and stretch the spring further. But the geometry was a right triangle, which is relatively simple, and led to iterating on 3 different equations for 3 different unknowns. We can work a similar problem using a general triangle, which is harder, but it's still doable. And that's what this problem is all about. So this problem is a general triangle where my system, at the original position of my system, was horizontal. And so there's a fixed length D1, and then an original unstretched length of the spring D2. And these are the inputs here. And I can input a spring constant. Once I hang a weight from this guy at point A, then this system will fall to an equilibrium position where the spring stretch and the entire system is in force equilibrium. I mean, it makes sense conceptually that you can do that, but the question is, how do you do it? And truthfully, it's kind of complicated. I mean, but that's why I'm showing it to you, so you can see how it's done. And once you see it, you go like, oh, I can do that. And again, to illustrate to you how you might use Excel to do it as well. So what equations can you write? So when you're in this general position, I have a stretch of the spring, which is L, which is greater than D2. I have an angle theta here. I have an angle phi here. This D1 is constant, and so it's the same as that original D1. So he doesn't stretch at all. Because he doesn't stretch, the path that A travels is kind of along a circular arc from the original position down to A. In other words, it doesn't move straight down. So at this equilibrium position, force equilibrium has to be satisfied. In other words, particle equilibrium has to be satisfied. So this is my free body diagram at point A. And so I have a force of the spring that acts at theta. And then I have a force that acts along this cable, which acts at phi. And I have the weight that I've hung. So I can write 2 equations of force equilibrium. So in the right direction, I've got Fs cosine theta minus P cosine phi is equal to 0. And in the vertical direction, I can write Fs sine theta plus P sine phi minus W is equal to 0. So I got 2 force equations. Unfortunately, I've got 1, 2, 3, 4 unknowns in those equations. Fs, P, theta, and phi. So I need at least 2 more equations. For the spring, I can write spring force, which is equal to Fs, mine is equal to K times stretch, and stretch is L minus D2. So L is the current length, D2 was the unstretched length of the spring. Well, this is great, except it introduces one more unknown. So it introduces the L unknown. So now I'm up to 5 unknowns, and I have 3 equations. So I still need 2 more equations. Well, I can write law of sines. Well, you know law of sines. Law of sines is, the sine of an angle divided by the opposite side is equal to the sine of another angle divided by the opposite side is equal to another angle divided by the opposite side. And so for this triangle here, I can say that sine of phi over L is equal to sine of theta over D1. And if I multiply through by the denominators, I basically get D1 sine phi is equal to L sine theta. I'm not sure that's exactly right based on this picture, but in my other notes, I'll show it to you. And then finally, I still need another equation, but I can actually use law of sines again and relate this psi to this length. And so I have D1 plus D2 times sine of theta is equal to D1 times sine of theta. I'm sorry, D1 times sine of psi, which in psi is 180 minus phi minus theta. And so this gives me 5 equations and 5 unknowns. So I'm iterating on F, the spring force, theta, phi, P, and L. And these residuals are basically the right-hand sides of these guys. When you have all of these correct, this right-hand side should be exactly 0. And then I square them, and then I sum the squares. And so ultimately, I'm using solver to minimize this sum of the squares. It's not going to be 0, but I'm going to minimize it. And so we can take W, this is currently W equal 30. Let's just put 20 here. 20, which is basically this guy right here. And let's launch solver. So we'll go to data and solver. And again, if you don't find solver, go to file, options, add-ins, and you want solver add-in to be checked. Okay. And so we click on solver. And so solver, we're taking the sum of the squares, which is currently 100. We're going to set that guy to 0. And we're going to tell solver to iterate on all 5 of these variables in such a way as to try to drive this to 0 if possible. And if you click on options over here, I've got a default condition of about 5.00005, a real small number. And just say OK. And just say solve. And it says, OK, we found a solution. Pretty small number. These are all pretty small numbers. They're not 0, so they're not exact, but they're not bad. And so for spring force, we got 23.73. And the last time I did this for 20, I got 22.1. That's off a little bit, isn't it? For theta, 21.8. Theta, 23.4. L is 2.47, 2.44. That's not very close. We're going to redo this. Okay, let's try this again. And so I'm going to copy this, and I'm going to paste as an image. just so we've got these numbers. And I'm going to do this again. I'm just going to take these as this. No, I'll change these. I'll go 24, 27, 22. Okay. So when you're iterating, you're oftentimes your answers and your convergence is a function of your starting guesses. So if you change the starting guesses, you can actually get a slightly different answer. The other issue you run into on this problem is when you're iterating on 5 different variables, it's harder to get a super precise answer. So you're going to end up with more variations in the answer uh, because of so many variables. Data solver solve. So this time I've got 22.3, 22.1. Theta is 23.16, 23.4. Yeah, so this answer here. So this set of answers is different than this set of answers, which is different than what I gave you here. So one more thing I'll try is I'll improve the residual. I'll go O1. I'll make it slightly tighter. Solve. Okay, so this is a tighter constraint here. And now I'm at 22.24 compared to 22.1, 23.2, 23.4. So this should be a little bit better answer because this is a tighter tolerance. I don't think it'll work, but I'll try even tighter tolerance yet. So I'm going to go point another 0.5. So it wasn't able to converge. So we're at 22.2, 23.2. So each time you do this, depending on your starting numbers, you're going to get slightly different numbers because there's a little bit of error from every one. Every one of these has a exactly correct number. But the fact that we're iterating on 5 of them prevents us from getting the perfectly exact number. So all we're getting is these guys are really, really close to one another. But the algorithm will end up with slightly different numbers, which are still within that bracket that will give us a fairly tight tolerance here, but you end up with different numbers each time you do it. So if you're comparing yours to mine or mine to yours to somebody else's, we're not all going to get the same numbers, but this will get us in the ballpark anyway. And these residuals are like times 10 to the minus eighth, so they're not bad. I mean, these are all valid equations, and they should be exactly zero if the numbers are exactly correct. Well, these are like 10 to the minus eighth, so that's pretty close, actually. So again, what you expect is the heavier weight that I apply here, the farther this guy's going to fall, the greater the theta, and the greater the fall. And that's basically what you see here. Theta is the blue, and orange is the elevation change. It's L sine theta. And so this is kind of what you expect. And that's actually kind of cool that we basically built a mathematical model for this particular system that models not only the force equilibrium, but also the geometry of the problem as you apply those forces. And so that's powerful. And so Excel is a powerful tool. And this is just kind of a brute force goodness of fit that we set up, but this is something that you can do for other types of iteration problems if you wish. And you can use, for simple iteration, you can use goal seek if you're iterating on one variable. But if you're iterating on two or more variables, then you have to use solver, which is extremely powerful. So